So, oh, this meeting is being live streamed.
No, it's being recorded as a unlisted video, so nobody has the link to it. But yeah, it'll be stored in case they want to refer.
Okay, sure. No, I don't have a problem with it. I just was surprised.
Yeah, that just popped up. It's being streamed as unlisted, right, Shiva?
Yep.
Okay.
So the idea would be, have you guys covered how to, well, why is the neutrino actually important in a beta decay experiment? Have you guys started with that?
Yeah, because I think it's conservation of lepton numbers.
Not really. I mean, you would still need it basically to match experiment and theory.
Yeah.
If it was just a two-body decay, then the beta decay, so you would expect your electron to always have a fixed amount of energy that it carries away. But because it's because it's actually a three-body decay, you have an invisible ghost particle called the neutrino, which is also produced. The energy of the resulting electron plus the neutrino has to be constant. So your distribution of energy of the outgoing, the daughter electron is not going to be constant. It's going to be a distribution. So basically, it's a two-body versus three-body decay problem, energy momentum conservation in that context. Does that make sense?
Yep. And there is also another way of discovering it, no, Shalini ma'am. Like, I heard there is another way, like using one chemical or some detector type, they can discover the neutrino interaction. Like simple one. Is there anything like that?
Actually, so most neutrino, I shouldn't say most neutrino detection experiments. Again, I don't remember which one it is, but one of the Kamiokandis. What they use is a Cherenkov detector. So you have, again, I need to look up the specifics of this. You have the main body of the detector filled with, I don't remember, one of the one material. So when neutrinos are interact with it, if it's a electron neutrino which interacts with the material, an electron is produced, and if it's a muon neutrino which interacts with it, a muon neutrino is produced. And in this material, the speed of the produced electron or muon is greater than the speed of light in the material. And because of this, it gives out a cone of radiation called Cherenkov light, which is different for an electron versus a muon. And this is how you can distinguish which particle was the guy who interacted with it in the first place.
It's accurate.
Is Cherenkov radiation given off only by charged particles?
Right. So you have electrons and muons, both of which have negative -1 charge.
Yeah, no, I'm asking, is it given only by charged particles? Is what I'm asking.
Right, it is, yeah.
Okay.
Let me see if I can find a figure somewhere. It's quite pretty. Cherenkov ring, I think it's called.
And experimental people who are interested in that make note of these points, no?
Okay, so this says it is neutrino interaction in water. Okay, let me see if I can share my screen. Okay. So, should I have clicked? Okay, can you see this diagram here?
Yeah.
So it says interaction in water. Now, I don't remember what exactly is the content of the detector, but when you have a muon that is produced, a muon neutrino would interact with the substance, in this case, as it says, water, and a muon is going to be produced. And the muon travels faster than the speed of light in water. So it leaves out this ring, which is usually a clean signature, compared to electrons, which will have a more diffused ring. So this is how you can collect the light from this using PMTs, and finally, be able to sort of measure the flavor of the incoming neutrino. So this is one way of actually, well, seeing the neutrino. But as far as I understand, it was first theorized in the context of beta decay. So why do you need it in the first place?
Okay, I don't really know if that was the question. Yeah, Sagar, go ahead. I think someone is speaking.
Why only muon is ejected or decayed from electron neutrino, muon neutrino? Why is that? Like, why muon neutrino produces muon particle, and why electron neutrino produces electron? Is there any
As far as I
reason?
understand, that has to do with the conservation of the flavor. I think has to be conserved. No,
Yeah, the
sorry,
flavor has to be.
lepton number.
Yeah, exactly. Le and LB.
Yeah, it has to be
I think it's
conserved.
L. It's L, I guess.
Actually, we know that it is because of lepton numbers. It is that what actually causes this lepton number conservation? Why is that present actually?
A good question. Now we don't know the answer to why lepton number needs to be conserved, but this is one of the assumptions that you have made. In fact, there are theories which go on without conserving lepton number as well. But within the scope of the standard model, it's one of the assumptions that you make, as far as I understand.
Okay.
It's like energy conservation. Why do you have to conserve energy?
So there are like derivations that can prove that lepton numbers have to be conserved.
I think Aditya showed in his PPT, like if something invary, then it has to be conserved like that. Aditya was it something like that?
For lepton numbers specifically, it's an empirically observed fact. There is no derivation per se. I mean, based on what I've read, other stuff like charge and stuff, prove that under symmetry they are conserved. But lepton number per se is an empirical fact that is written into the standard model. It's an assumption, as she said.
Okay.
Right.
So I think one group can also work on why this conservation laws are present.
Like in general, lepton numbers I think are conserved, but like generation and flavor wise is an empirical fact.
I think it is also got from the Gates theory, isn't ma'am? The Gates theory.
Again, I am not 100% sure, but it would be the result of some sort of symmetry. Lepton number conservation would come out as as the result of some sort of Gates symmetry, I would say. I shouldn't comment on this because I'm not very sure. But I was looking at Wikipedia right now, and it says that neutrino oscillations, in the case of neutrino oscillations, clearly lepton number cannot be conserved because, you're changing from one lepton to the other. And there are also searches for beyond standard model physics, which look for lepton number of flavor violation. So you have a muon trying to decay into an electron. So those theories also exist, but we have placed very tight bounds on it, saying that, okay, but the chances of this happening is very, very small. The chances of a muon decaying into electron is very, very, very small. So, yeah.
So I had a question actually. So the thing, like, what are the, and in the scope of the project, like, can we investigate on like neutron mass spectrum, like normal spectrum or inverted spectrum, like differences between the masses of lightest neutrinos and difference between the heaviest neutrinos? Like, do we need any background as such for that to investigate it? Assuming that I have kind of postgraduate level of quantum mechanic background a little bit.
I'm not sure if I'm the right person to answer this again because I haven't specifically worked with neutrino experiments, but understanding whether the neutrino mass spectrum is straight or inverted would be, you would have to look at experimental results to do this. So you have the two mass differences and you have the three mixing angles, and these are quantities that can be experimentally measured from the data, and this can eventually be used to determine whether the mass spectrum is straight or inverted.
So like, do they happen? I just have a question. Like, this normal or inverted, like they kind of happen, or do they always present themselves simultaneously? Like, or we have to investigate that matter of fact that it will be a normal or inverted, or is
So
it
you
a
have to
given kind of?
investigate that.
Okay.
So right
So
now, what you can measure is the mass difference between the, say, electron muon, two of the three mass differences, as far as I understand, you've been able to measure very precisely. Now, I'm not updated with these results again, but what you have is a mass difference, and that is why you need to know in what order these guys are arranged.
so based on
And
that
in
order,
reality, only one of the two is possible.
okay. So based on the order, we determine is it a normal or an inverted spectrum, right? Is it
Exactly.
the thing? Okay. So assuming that we kind of, as a starting point, neutrino oscillations in vacuum, where can we take it further? Like after that, what will be the next point? Like after neutrino oscillations in vacuum, like we have discussed this about the mass spectrum, and anything else like.
Well, when you say neutrino oscillations in matter, have you discussed two flavor oscillations or three flavor oscillations?
Okay.
So you can do two things. You can assume that there are only two flavors of neutrinos which can oscillate into each other, and you can determine the probabilities for one flavor going into the other as a function of the total distance it travels and the mass difference and the energy of the beam. So that is, I would say, the first thing that you would want to calculate. And after that, what you can do is look for a little more. So this is stuff that you can plot out and try to see what the function looks like, finally, the probability function. The next step to proceed would be still sticking to two flavor oscillations, but trying to get this into a more realistic scenario. So basically, three flavor neutrino oscillations, which is the realistic case, reduces to the two flavor case. It's a good approximation because the mixing angle of, again, tau with one of them is quite small. So because of which the two flavor case is actually a good approximation to the three flavor case. So what you would, I would suggest you could do next is to take it in a little bit into the real world. You can, instead of having a beam of say electron neutrinos all with the same energy, which is not a realistic case, you could smear the beam, sort of make it a Gaussian beam. So your mean is still at the energy of that you want, but you will also have neutrinos with slightly lesser or slightly higher energy than the mean energy that you desire. And you could see how the neutrino oscillation probabilities change. The idea of the interesting thing is that it is without any beam smearing, I would call it. You will have a sinusoidal function that goes on for infinity. But if you have a Gaussian sort of beam, then the probability function will eventually start to die down. It becomes sort of like a damped oscillation. And that is something that is very interesting to see next.
Okay, so I kind of got this idea. Yeah, I think this sounds very nice. I think this is like a kind of achievable task, I guess. What you have a little bit in the scope that we are doing. So for that, like, can you just give me outlines, like any step to proceed from? Like the starting point obviously will be neutrino oscillation in matter, and that will be two flavor oscillation, and then will be this experimental beam smearing that you're saying. So
Right. So the next step would be to basically just plot it out. Just plot it out and see. So for different, find out the, say, you have the probability for a neutrino, electron type neutrino going into a muon type neutrino. And then that is a function of a mixing angle between the two, the mass difference, the length that the neutrino beam travels, and the total energy that you started off with. So the idea would be to find out the mass difference and the mixing angle from experiment. So these numbers you can find on the internet, and plug these in. And then as a fix the energy of the beam and see how the probability changes with the distance that the beam travels, fix the distance it travels, and change the energy of the beam. Say at 1 kilometer, if I want 100% probability, I want 100% of my electron neutrinos to turn into muons, what is the energy at which I should shoot my beam at? So those kind of questions you can ask yourself.
Yeah. Okay. Thank you.
And once you're comfortable with plotting this out, for smearing the beam, sort of giving it a Gaussian distribution, this can be done numerically. So if you're good with Python, for example, this would be a very straightforward, basically any language in general, this would be a very simple Gaussian distribution that you can convolute sort of with this probability. The convolution is something that can be, well, it's directly there in Python, for example,
Yeah.
and
Okay.
then derive these. Yeah,
So,
that's one thing you
do
can
you
do.
mind asking like any starting literature point for this? Do you have any idea? Like what should we like kind of search for this to take on for the literature to kind of, if you want to survey on our own? Any starting point for this?
Let me note this down and I'll search in the meanwhile and I'll get back to you.
Yeah.
I'm
Thank you
not
very
quite
much.
sure if I know.
Thank you.
No problem.
Also, I think her report must have a bunch of references in the end. So maybe that that could serve as a source as well.
Yes, I have just opened my report and I am looking at. Yeah, there is a bunch of. So, has the report been shared with everyone, Sitara?
But yeah, the people here, they have gone through it. Most of them have. They have access to the report. Yeah.
Okay, so they're basically what the idea that I was suggesting is right from my report, the way I proceeded in my report, that is one of the ways to go.
Yeah, I think Abhishek kind of went through it. I think that was Abhishek, right? Yeah, so if you had
Yeah.
more specific questions from her report, I remember you had certain places that you were not able to get. So now would be a good time.
Yeah, the dark matter part I couldn't comprehend. Like apart from that, like I just could I didn't read obviously didn't read the through detailedly, like the mathematics part. I just kind of skimmed through the report, and but the like my background was a little bit weak on the dark matter as a candidate part. That part was a little bit shaky for me. And apart from that, the basic theory I could kind of comprehend because that was like a little bit easy, like to understand.
Right. I understand what you're saying, and I think it's completely understandable because I have not been super clear with what exactly is why and how to motivate these dark matter candidates, and neither gone into a very good detail on why I'm picking up supersymmetry. Now, the point was I didn't really know a lot of it at that point of time. I still don't as much. But basically, your idea is that there is a theory of supersymmetry which tells you, okay, there exists a particle, if supersymmetry is correct, there exists a particle called a neutralino. And the neutralino is, well, because of its mass, I would say, of say predicted masses and so on, this is one of the candidates that can possibly make up a dark matter. It is a weakly interacting massive particle, so it has gravitational interactions as you need it, and it has weak interactions. By weak interactions, it means that it can decay into electrons, not directly electrons, mostly electron neutrinos. Now, supersymmetry, there are two kinds of supersymmetry, many kinds of supersymmetry. The neutralino that we're talking about for as a candidate for dark matter comes from something called R parity conserving supersymmetry, as far as I understand. So R parity is yet another symmetry that is introduced. For standard model particles, I think it's -1, and for supersymmetric particles, it's +1, the value of R parity. And basically, it says that if you have the total amount of parity in the initial state and the final state should be the same. So if you have, say, a neutralino which has +1 R parity, it would decay into two standard model particles, both with -1 parity. So in the final state, parity goes basically as -1 into -1, which will give you +1. So stop me if this stops making sense at any point. So basically what you do is you have two neutralinos that would, well, these are heavy particles. So the idea is that they would accumulate at the center of large bodies like the Earth, like the center of different galaxies, like the sun. I'm not sure what exactly is the name for this theory, but it says that they are going to annihilate after they reach a particular density, and this annihilation is going to produce neutrinos, which are going to then head toward the Earth-based detectors. The idea is just basically that. So I have not gone into details on how the neutrino looks like or what it does or how is it produced.
Yeah.
Mm-hmm.
So I think, yeah, it's yeah, but basically I don't have the background in that, so maybe I couldn't comprehend much of it, but yeah, I could make something like little bit. The motivation I could understand the motivation behind that. Yeah.
It's a little hand baby. I have to agree. It's a little hand baby.
So any specific mathematical background to require before that you kind of explain this all procedure. So any specific mathematical background, like apart from the standard stuff, to kind of dive into this problem?
Not really, but I would suggest, if possible, having sort of the basics of group theory. That is one thing that I really lacked when I did this project. And the basics of group theory will help you understand why something is being conserved, why it's something not being conserved. It will give you just a slight bit more insight into what is going on. So if possible, you can cover that, but it's not a compulsory thing, not at all.
Okay. Yep. Thank you.
No problem.
Ma'am, I have one doubt.
Mhm.
So that is, we know that dark matter interacts only through gravity and it has mass, isn't it? But that means that we know Higgs field gives mass to particles, Higgs field. That means
Mhm.
Higgs field, which is a standard model particle, is interacting with some particle which is not in the standard model, and it is giving mass to that particle, isn't it? So how can we get a conclusion on this? Like, how can Higgs particle? I mean, the Higgs field can interact with a particle which is not yet detected, or how can we understand this?
That is a very good question, because so the proposal is that the Higgs field gives mass to standard model particles. That is the exact statement of the Higgs field. It does not say that the Higgs field is the only guy that gives mass to particles. So now there are extensions of the standard model where there are up to 5 Higgs bosons, all of them responsible for giving mass to different guys. So possibly in some extensions of the standard model, there exists another Higgs boson, which would possibly give mass to the dark matter particle. Nowhere in the standard model have we claimed that it is this Higgs boson that we found at 125 GeV, which gives mass to everyone. There can be a different mass mechanism as well.
Okay.
On that note, one more thing that we don't understand is neutrino masses. The Higgs boson does not give mass to neutrinos. That is not covered within the standard model. And we don't know how neutrino masses are generated. There might be
Even
another
I had
Higgs
that
guy.
doubt. Yeah, even I had that doubt, like why neutrino is not having a definite mass.
It is not covered under the standard model, but I don't really know why. I don't really know why exactly, but it has something to do with, again, gauge symmetries, as far as I know.
Okay. So we covered for theory 2 discussion till now. So we got so many ideas like isn't conservation of lepton numbers are violated in neutrino oscillation? Why neutrino is not having definite mass? Two neutrino flavor oscillation, and many ideas we got. So I think we can go to discussion for theory one group, no ma'am, like the astrophysical aspect of neutrinos. Can you give anything on this?
On the astrophysical aspect, I don't know, frankly. I've not kept up with the astrophysics of the neutrino. So,
Yeah, I think theory one can be a combination of studying the astrophysical sources. But like you said, just to clear it up, the study of neutralinos is going to require pretty intermediate level quantum mechanics, right? Like they should already be fairly familiar with oscillations as well, and or at least, yeah, the mathematical prerequisite.
well, to actually understand what is going on with the neutralino and how the neutralino is actually, say, produced in the standard model, you would require much more than quantum mechanics, much more than that. So, within the scope of my report, what I've done is just assumed, okay, so this guy exists, what next? So, for that, you don't really need a lot of math or any understanding of QM.
Okay, cool.
Yeah. So like, but I think for oscillations, like we kind of need to know basic stuff, right?
Quantum mechanics, yes.
Yeah. For oscillation, the unitary operators and stuff. So I think that,
Right.
yeah, I think that might be, and to calculate the probabilities from them, a little bit of Heisenberg picture, interaction picture, stuff like that. I think little bit we
Yes.
need, little bit that background I think we need.
Yes, that you would need, I agree.
Okay, cool. So that makes sense. So what we can do is kind of make the dark matter candidate thing part of the first group. Second group, yeah, would you want to elaborate on, I guess, estimation of neutrino flux and how that works from a detector point of view, or how you would visualize this?
Frankly, I don't know how it would work with an actual detector, because what I did was to, well, simulate the decay and then look at, basically it's a package that tells you this is the flux as a measure of say distance, or as the measure of energy of the neutrino. But in a real detector, how they would measure the flux, I don't know. But going back a step, I would suggest to concentrate first on doing everything that you can with two flavor neutrino oscillations. Like I said, smear the beam out, see how these probabilities change. Look what happens when these two flavor probabilities, how do they change when the beam is traveling through matter. Extend it to the three flavor case. I think doing all of that will possibly be more education, I mean, give you a little more insight into what is happening than going into the neutralino part. That would be more accessible with basic quantum mechanics.
Okay, great. And for this is what you used WIMSIM for, right? The WIMSIM stuff.
Right. So, but that was completely to look at dark matter. But that was after you're sure, okay, I understand what neutrino oscillations are actually happening. How do they happen?
Okay. So till there, Python would suffice then. Is that what?
Yes, till then, Python is good. C++ is good. GNU plot, if you have the very basics, that is also good. Basically, you need anything that can plot things out and anything that can do a convolution integral. Convolutional integral. I don't know how to pronounce it.
Okay.
Convolute basically two functions together and integrate the output. That is all you need, really. Any software.
Okay, that sounds doable. So I think I would suggest maybe Abhishek to kind of elaborate on this, like each of the points or each of the steps even, and the theory 2 group can follow this particular path.
Yeah, as what I understood is that first we need to kind of narrow down on neutrino two flavor oscillation, kind of understand it. And next we would have to look at the, so yeah, two flavor neutrino oscillation, and then look at it like to find of first understand the mixing angle, the mass square difference, and to look at some and how does the probabilities depend on these parameters. And I think if we can come until there, then as Shalini ma'am has said, we can kind of plot some results on two flavor oscillation probabilities using these parameters, like some parameters like she shared, like the initial energy and how does the probabilities depend on the energies. And we can kind of correlate with the existing experimental data, and we can see that if are we able to kind of correlate these results.
Okay, coming to, okay, I'm not sure about the last part. We were supposed to have some kind of small data exercise. Do you think that's going to be possible, Shalini? At least for perhaps, I'm thinking group 2 and 3.
I'm still looking into it because the idea was that you would want to do minimal setup as possible. Basically, so that you can work with the physics aspect of things and not with the computational and all of that stuff. So what I was looking into is a software called Docker, in case anyone has already worked with Docker before.
Yeah, so we have Jeevan here, who's a software developer, and he's with us, and maybe he can help out if we have a small session with just the 4-5 of us. And if you need help, he'll be able to set that up.
Okay, so with Docker, what we can basically do is package everything into a tiny environment, everything that we need, and share that with the students. So I did not get a chance to look at Docker yet, but if that is set up, then well, you can do a basic exercise on either, say, particle physics, discover a particle, or you can do the Vim sim exercise, for example. But I am not so sure if that can be done over this week because I am not super free.
Yeah, that's not a problem. I think this data exercise could be maybe 2 weeks from now, or rather the next week, basically, because this week they already have a structure for what to do next. That won't be an issue. Let's see, if not next Sunday, sometime after that, we can sit down and put the Docker thing into place. If that is feasible within, say, an hour's time. If it's too complicated, it's okay. We don't have to do it.
Okay,
All
I
right.
will get back to you again on that. And there is one more thing that I just realized I can share with you, which would be very interesting. So I've shared a link with you on the chat. This is basically a bunch of seminars called ASP Online Seminars, and they cover a lot of things from particle physics to astrophysics. There was a series in the past on neutrino oscillations as well, neutrinos in general, and we can possibly look that up. But this is something that maybe you guys can keep in sync with. Basically, see when there is an event coming up and attend these. These are free to attend. They are with basically, say, basic knowledge of just two flavored neutrino oscillations, and only that bit. You can still understand the results that they're trying to present on, say, what is the current status of measuring the mass difference or the mixing angle, including, well, what is the status of different experiments that are working with neutrinos.
Cool. That would be really interesting. I actually gave them a resource a while ago, I think for a particle physics series of lectures. I'm not sure if these guys have tuned in. I think it was by, I'm not sure, maybe Kavli, I don't know. But I think on, day one itself, I'd shared a lecture series with them. Okay.
I share another link right now. It's called Neutrino Physics at Accelerators. Now, these are, there's a 3-part series from what I understand, but these are done in the past, but there are recordings available. To check this link, you'll have to make an open account, which is okay, I think. But again, these are resources on Indico that people, well, they give regular lectures on these things, and it can be useful for basics.
Great. Okay, I remember you talking about, I think the seesaw phenomenon that was, I'm not sure if that's part of your report, but would you like to kind of elaborate on that if some people are interested?
Okay, so The idea is that within the standard model, you don't know how the Higgs boson is not the guy who gives neutrino masses, because well, the standard model started off with the assumption that neutrinos are massless. So you need to now the idea of the experimental observation of neutrino oscillations points to the idea that neutrinos have masses. So now you're at this crossroad where you need to find a way to give masses to these neutrinos. And one of the theories that exist is called the seesaw mechanism, where for each neutrino you have sort of a really heavy partner. And so it literally works like a seesaw. The neutrinos which are there in the standard model that you see are on the lower end of the seesaw, and the higher end of the seesaw, and there is a fat partner neutrino which it's on the other side. So because so there was some symmetry that was broken, because of which one became super heavy, one became super light. The super light is the guy that you see as your standard model neutrino. The other three guys are supposed to be theorized to be present. And the seesaw, this is called the seesaw mechanism. You have two guys sitting on a seesaw. One of them is super heavy, one of them is super light. This is one thing that you can possibly explore after, well, getting confident that you understand what neutrino oscillations are. It's one of the mechanisms by which you can generate masses for explain the very light neutrino masses.
Okay, so I hope some of you are making a note of that, and I think that will be interesting towards the end of the project. And one more thing is like if they were considering just the ice cube experiment, I think there's a third group who will be going with the theory and learning about oscillations as well. But if they start to work backward, I think you mentioned that it's possible to estimate the flux at a detector, right, given its location and things like that.
Right. So this is using the WIMSIM package for specifically that theory where you have neutralinos that are produced and they decay. So that you can use to check the total flux at any ground-based detector.
Oh, okay. I mean, on a more general note, if you just had to calculate the number of neutrinos you would detect in a year, that estimation can be done, right? So
right, I think it can be done. Yeah,
okay.
I think it can be done. I mean, that would be back of the envelope sort of calculation. You don't possibly need to simulate anything.
Whatever that figure, that number you would get per year, I think that is possible. Just as a small exercise. Okay, so that's one more thing you guys can make a note of. We have just about 10 minutes more, guys. If there are any open questions, now is the time to ask.
I'm spamming your chat with a few links as I find them. So in case you guys are interested, you can check these out.
Why do another question? I have a question. Why do people care a lot about, say, parity violation or CP violation when there's a more supposedly fundamental CPT symmetry that is supposed to hold throughout no matter what?
The idea is that, well, we have made a bunch of assumptions. All your theories have a bunch of assumptions that, hey, this is conserved, that is conserved. And now you're testing these assumptions to make a statement on, yes, this is conserved, or yes, this is not conserved. If it is not, then do you have a better theory? You try to look for things that may point towards the fact that, yep, there is a better theory. So the idea is just to test your assumptions by looking for any sort of violation. For example, if you have, so there are experiments which try to measure lepton flavor violation. So you have lepton, an example of a lepton flavor violating decay would be where the muon goes into an electron and say a gamma. And this is something that is forbidden within the standard model. And so what you do is you say, okay, let me look for this process. The standard model says it's forbidden, then under that assumption, this process should not exist. Now, if you see that it indeed does not exist, you're like, okay, the standard model, it is in agreement within the standard model. But if you see that this is not the case, you know that the standard model is not enough as a theory of, well, particle physics, and you need to look for something better than that. So you try to modify your theory.
Cool. Are there more questions? I also wanted to add, Stone has that, Stone is also working on dark matter detection, right? So some of you who are more inclined towards studying, you want to know more about dark matter, maybe you can just pick that up, go over even just the documentation that Stone has, and if you just want to work on it conceptually, that's something you can. There are a lot of things within CERN that offer a lot of food for study and thought.
Hey, I have.
Yeah.
Yeah. So I was thinking we could maybe focus on cosmic neutrino background, probably its properties or evidence of their existence. Is there anything you're aware about cosmic neutrino?
Sorry, can you repeat your question again?
Okay. So I thought we might be able to focus on cosmic neutrino background and its properties and basically uh, their evidence of their existence. If you have, do you have any idea about that?
Sorry, I don't have an idea about that, but yeah, I mean that is something that you can explore. Yes.
I remember reading up about this, and cosmic neutrino backgrounds are purely only theoretical right now. There's zero evidence. Actually, the theory even states that the energy levels of those are so less that we possibly might not even be able to detect it like ever.
Mm-hmm.
That makes sense, actually.
Interesting.
Like since neutrinos react like weaker with matter than photons did, the whole idea of the cosmic neutrino background is we could get an image of the universe when it's like 1 second old. Like since it would escape far earlier than photons and far before the cosmic microwave background. But the theorized energy levels for that is like order of 10 to the minus 5 electron volts or stuff, something like that. And detecting that would be like really hard right now.
But
Yeah,
I
the
was
best
thinking
you
Right.
can
at least the theory we could focus on. I mean,
yeah, best you could estimate it or something like that.
Okay, so again, I'm gone to Wikipedia for this, and it says that there is very strong indirect evidence that it does exist, the cosmic neutrino background. But yeah, as Aditya, I think, said that they have very low energies. Yes.
I think it can
But
be a good exercise for theory one group, no? Cosmic neutrino background, neutrino flux.
Yeah, they can add it in part of their article. So yeah, just make a note of it. There was something else I wanted to say. Yeah, so maybe by the end of it, since they're studying particle physics and about, I don't know, maybe 60% of them are very new to the field, they can also learn about how things are modeled, how things are done actually. So if you want to talk about the software tools that are very specific to particle physics, you can just send us a resource maybe or whatever. I think you spoke about Root and Gent4, and a lot of people have not even heard of it. So first of all, why does it necessitate such specialized software tools? Would you want to comment on that?
okay, sure. So, well, I would have to first stress that before going into looking at any software, the idea would be to look at what the standard model is. I mean, theoretically, looking at the mathematical aspects of it to understand better why you would even want to simulate stuff like this. Now, going into software, you have multiple different levels at which you need simulation. You start off with simulating your detector. For this, you have softwares called, one of the softwares that you have is called Geant4. It can help you to model the different materials that are there in the detector and basically model detector response as different particles fall on it. Then you need to also be able to model the proton-proton collisions, for example. So, and you need to be able to produce the final hadrons. So when you have a proton-proton collisions, what actually happens is the quarks or the gluons inside the protons are the ones that actually collide with each other. You have different particles that are produced, you have different other well, at the most basic level, you have quarks and which are produced, but these quarks cannot stay floating around. So they are going to always combine into color neutral states and form hadrons. And these hadrons are the ones that will hit your detector. So you need to do two things. Number one, you need to understand how to get these two protons to interact with each other. For that, you have softwares called, for example, MadGraph, Pythia, and then you need to have a second software which can do the hadronization, where these quarks are going to form hadrons, color neutral particles, and these hit your detector. For that, you again have specialized software. Usually Pythia is the one that is used for this. So now you have simulated the particle collision, you have simulated the detector, but now you need to measure what happens at the end. For that, for example, the example that I had shown in my talk, if you need to have you need to measure the invariant mass of the 4 leptons that are produced. If you want to look for, say, the Higgs decaying into 2 Z bosons, further decaying into 4 leptons. So to find the Higgs in that particular channel, I would say, in that particular diagram, you would need to calculate the invariant mass of the 4 leptons. For this, you need to form sort of a histogram. Different events, you pick up different events with 4 leptons, you add up the masses, and you find a number. And then you bin these all these numbers, and max you should see a peak around the Higgs to 4 lepton channel. You would expect, if it actually exists, you would expect to see it. So this histogramming work is done by yet another software called Root. So that is the end user software, which most of us experimental physicists would use. Some of us also go into, well, making the simulations, that those are called Monte Carlo, basically Monte Carlo generators, but it's not, we don't participate. I mean, at least in my analysis group, we don't participate in that as much. Yeah. So these are, well, some of the softwares that we use.
Cool. So, yeah.
I'm sorry. Can someone type it in the chat box, the different softwares as streaming, just to know about them, like not in detail, just to read about them?
Sure.
Thank
Let me put this there.
Yeah, I think this is something pretty novel to a lot of us here. So, yeah, Shalini, if you do feel there is any one software that you think they can get acquainted with in a span of, say, 1.5 months, then just suggest it to me later.
Okay.
Or, yeah, just in terms of developing familiarity or playing around with it.
Okay. Okay, I'll get back to you on that, I think.
Cool. So I am going to jump because there's another meeting now. But if Shalini, I think we can end for today. I'm not sure if you're available next Sunday. What we can do is you can let me know any time of the week when you're available after the next week. So we can do that in case Sunday is not feasible for you.
Sure, it would usually be one of Saturday or Sunday for sure. I think I should be there, but in the off chance that I'm not, I'll tell you way in advance.
Okay, no problem. And guys, I think the format from the next week onwards can be kind of the first 20 minutes can be updates from all of you. So depending on which cohort you're in, please put together kind of like an update sheet at the end of the week, and that will quickly help you clear questions or let her know what is happening. Okay. You can just, each of you can summarize your group's progress in about 5 minutes. Cool. Thank you so much, Shalini. That was really helpful for all of us. So if there are more questions, guys, put it on the group. I will make like a collection of them and send it across. Okay. Especially, I think once you dive into the project, that's where you will encounter more questions or doubts. So
One more thing I can do is leave my email address over here. So you guys can actually send me questions, and I don't think there were many questions I couldn't satisfactorily answer today. I can give them a shot again on email. Um, let me put my email address here. Yeah. So you guys can ping me, and I will try to get back to you with questions, answers.
cool. Thank you so much. We can close for now. I guess from the experimental side, Shalini, if you have some online resource, I think CERN website itself is really elaborative. If some of you have not explored it yet, it has really a lot of information. But otherwise, if you guys want to focus on Ice Cube and stuff, let's see if we can find some comprehensive resource for that. But I think the other teams, so we'll have another meeting to clarify the problem statement with a little bit more clarity. We'll just have a discussion for the whole team once we, get into the division of course. Okay. Yeah, that's it. Any general advice, Shalini, as they kind of enter, I don't know, their project from this week onwards?
Well, two things. Whatever you pick up, try to explore it to the max depth possible. And once you learn a concept, try to explain it to somebody else, because, well, that is when you realize, when you try to explain things to somebody else, you start realizing the gaps that you have in your own knowledge. Well, that happened to me while I was trying to prepare a talk for you guys. And that really helps you understand the topic much, much better. And the second thing is to have fun. If you are forgetting to have fun, then it's not worth it. So, yeah.
Thank you so much. And I think the first thing she said, guys, please help each other out. There are people here who are probably just starting their undergrad, whereas some of you have a master's level experience. So please keep the knowledge transfer going throughout the week. We will not be kind of facilitating everything henceforth. So yeah, keep that going.
You can form teams of two, for example, 2 or 3, and just meet once a week, or just talk to each other. Hey, this is what I learned this time. And the other guy can ask you questions. Okay, do you blah, blah, blah. Just a question answer, just as you're catching up over coffee. That is something that really, really helps getting insights into many things.
Yes, buddy system. Cool. Cool. All the best to everyone here. I think till now they were just kind of prepping. So all the best. I think, like she said, please be thorough with what you study, kind of as much as possible, I guess, go into the depth of it. So yeah, we'll see you soon. Shalini, just let us know about Sunday's availability. Otherwise, it's cool. You don't have to, yeah.
Absolutely.
Whatever.
I'll let you know. Thanks a lot.
All right. Thanks,
Thank you.
everyone. Good night. Yeah.
Bye bye. All the best.
Thank you.